the jet that changed everything. In the spring of 2011, grainy photographs began circulating across defense forums and intelligence circles that sent a quiet shockwave through every Western Air Force on the planet. The images showed a large, angular, twin-engine fighter aircraft taxiing at Chengdu Airfield in southwestern China. It had the unmistakable silhouette of a stealth design, faceted surfaces, blended edges, a smooth, continuous fuselage that swallowed hard lines and scattered radar energy in ways that ordinary fighters simply do not. Western analysts had known for years that China was working on something, but seeing it roll out like that, in daylight, at a real airfield, with real pilots, made it undeniably concrete. China had a fifth-generation stealth fighter. They called it the J-20, the mighty dragon. But here is the part that most coverage missed then, and continues to underexplain today. The J-20 is not just a Chinese copy of a Western stealth concept. It is not a reverse-engineered F-22. It is not a knockoff of the F-35. When engineers and analysts actually dug into its geometry, its surface angles, its inlet design, its fuselage shaping, and its aerodynamic priorities, they found something genuinely different. Something that does not map cleanly onto any stealth philosophy that Lockheed, Boeing, or Northrop Grumman ever publicly embraced. The J-20 has a radar cross-section profile that diverges from every Western stealth design in ways that are deliberate, sophisticated, and tactically significant. And when you understand exactly what those differences are, and exactly what they mean on a real battlefield, the picture that emerges is one of the most important strategic puzzles in modern military aviation. So that is what we are going to break down today. Not just what stealth is, not just how it works in general, but specifically, what the J-20 does differently, why those differences exist, and what they mean for any pilot or air force that might one day find itself on the opposite side of that aircraft. If you want to understand the future of air warfare, stay right here. And before we go any further, hit subscribe right now. Over 95% of people watching this have not subscribed yet. It is completely free, and it means you never miss a video like this one. Let us start at the foundation. Radar cross-section. Most people have heard the term. Fewer people actually understand what it means in practical terms, and even fewer understand why it is the single most important number that defines whether a combat aircraft lives or dies in a modern air battle. Radar cross-section, abbreviated as RCS, is essentially a measurement of how detectable an object is to radar. It is expressed in square meters. But here is the critical thing to understand. RCS is not the actual physical size of the aircraft. It is not how big the plane looks to your eyes. It is a measurement of how much radar energy the aircraft reflects back toward the radar receiver. An aircraft with a very low RCS reflects only a tiny fraction of the radar energy that hits it back toward the enemy system trying to track it. An aircraft with a high RCS bounces a strong, clear signal right back and lights up the screen like a billboard. To give you a sense of scale, a conventional fourth-generation fighter like an F-16, an Su-27, or a MiG-29 has an RCS somewhere in the range of 5 to 15 square meters from the front aspect. That is a strong radar return. Easy to track, easy to engage at long range with air-to-air missiles. Now compare that to a stealth aircraft. The F-22 Raptor, the gold standard of Western stealth fighters, has a publicly acknowledged frontal RCS in the range of approximately 0.0001 square meters. Some estimates put it even lower. That is roughly the radar signature of a metal marble. The difference between those numbers is not just large, it is decisive. It means that by the time a radar system capable of detecting the F-22 can generate a fire control quality track on it, the Raptor may already have launched its missiles and departed the engagement zone. But here is where it gets complicated. RCS is not a single fixed number. It changes dramatically based on angle. The frontal RCS of an aircraft, meaning the radar return you see when looking directly at the nose of the plane, is almost always the most carefully optimized aspect in stealth design. That is the direction the aircraft points toward the enemy when it is closing in for an attack or when it is trying to sneak through defended airspace. The side aspect RCS, the radar return from the flanks of the aircraft, is generally higher on every stealth design ever built, and the rear aspect RCS is typically higher still. But the relationship between those three numbers, how the RCS changes as you rotate around the aircraft, is where different stealth philosophies diverge in profound ways. And that divergence is at the heart of everything we need to talk about with the J-20. Western stealth philosophy. Let us talk about how America approached stealth design, because the philosophy matters. Every geometry choice on a stealth aircraft is the product of a theory about what kind of threats the aircraft needs to defeat, what missions it will fly, and what trade-offs are acceptable. The F-117 Nighthawk was the first operational stealth aircraft, and its design philosophy was almost entirely driven by one goal: survive long enough to drop bombs on high-value targets defended by the most sophisticated Soviet-era surface-to-air missile systems. The F-117 was not meant to dogfight. It was not built for air-to-air combat. It was a penetrating strike aircraft, and its entire RCS profile was optimized for that single mission. The result was a bizarre, angular, almost otherworldly shape that contemporary aerodynamicists genuinely believed could not fly without computer assistance. But it worked. Against the radar frequencies and operating modes of Cold War air defense networks, the F-117 was nearly invisible from the front. The B-2 Spirit bomber took that philosophy further, with a flying wing design that is arguably the purest expression of stealth geometry ever built for a large aircraft. The smooth, continuous surface of the B-2 eliminates almost every hard corner and edge discontinuity that creates radar returns. From the front, the B-2 is terrifyingly quiet on radar. It was built to fly deep into Soviet airspace and survive long enough to release its nuclear or conventional payload. Then came the F-22 Raptor, and the philosophy shifted in a critical way. The F-22 was not just a stealth strike aircraft. It was a stealth air superiority fighter. It needed to be fast, it needed to be maneuverable, it needed to engage and destroy other fighters, and it needed to do all of that while maintaining a very low RCS from the front quarter. The result was a design that achieved something extraordinary. The F-22 combined genuine aerodynamic performance with frontal RCS optimization so good that it could essentially choose when and whether to be seen by most radar systems it was likely to encounter. The F-35 followed with a somewhat different balance. The F-35 is a multi-role aircraft, optimized for a broader range of missions across 3 service variants. Its RCS is somewhat higher than the F-22, though still dramatically lower than any non-stealth fighter. But critically, the F-35 was designed to be what analysts call broadband stealth, meaning its low observable characteristics were engineered to perform across a wide range of radar frequencies, not just the narrow X-band frequencies used by most airborne fire control radars. The thread running through all of these Western designs is a consistent priority. Drive the frontal RCS as low as physically possible. Accept a higher side and rear RCS as an engineering compromise, and design the aircraft around the assumption that it will primarily face threats in the forward quarter, from enemy radars looking straight at the nose of the incoming aircraft. Now let us look at what China did with the J-20, and why it is different. The J-20 is a large aircraft. That is the first thing that jumps out when you see it. It is considerably longer than the F-22. Its overall dimensions are closer to a heavy interceptor or a strike aircraft than a pure air superiority fighter. At roughly 20 meters in length, it dwarfs the F-22 at about 18 meters and the F-35 at about 15 meters. Its empty weight is estimated to be in a range that puts it firmly in the heavy fighter category. Why does size matter for stealth? Because in general, larger aircraft have higher RCS. Every additional surface area is a potential source of radar reflection. The J-20 designers knew this. They chose large size anyway. That choice tells you something very specific about what the aircraft was designed to do. Look at the J-20's frontal aspect. From the nose forward quarter, the design shows clear evidence of sophisticated RCS management. The fuselage is carefully blended. The canopy is shaped to scatter radar energy rather than reflect it back. The engine inlets are designed with carefully shaped serpentine ducts that hide the radar reflective compressor faces of the engines from any radar looking in from the front. On a conventional fighter, those spinning compressor blades are one of the strongest radar return sources on the entire aircraft, the J-20 blocks that return with precision. The weapons are carried internally, in fuselage bays, exactly like the F-22 and F-35, eliminating the external pylons and missiles that would otherwise create significant radar returns. The leading edges of the wing are carefully aligned so that radar energy tends to be reflected in specific narrow directions rather than broadly scattered. This edge alignment technique is common in Western stealth designs. The J-20 uses it with sophistication. So, from the front, the J-20 is genuinely stealthy. Not necessarily at the same absolute level as the F-22, but genuinely stealthy. That matters enormously in the context of how modern air-to-air combat works. But now look at the angles where the J-20 diverges from Western philosophy, and this is where it gets fascinating. The canards. This is the single most talked about and most misunderstood feature of the J-20. Canards are small, forward-mounted wing surfaces, positioned ahead of the main wing. They provide additional lift and dramatically improve maneuverability and pitch control. The J-20 has canards. The F-22 does not. The F-35 does not. No current production Western stealth fighter uses canards. Why not? Because canards create additional surfaces at additional angles. Every surface on an aircraft that is not precisely aligned with the primary edge alignment of the design is a potential additional source of radar reflection. The angles at which canards meet the airflow, the way their leading and trailing edges interact with incoming radar energy from different directions, all of that adds complexity to the RCS profile and generally increases it compared to a tailless delta or a conventional tail design. Western stealth designers looked at canards and largely concluded that the RCS penalty was too high. Chinese designers looked at the same trade-off and reached a different conclusion. They accepted whatever RCS contribution the canards make in exchange for what the canards give them: enhanced maneuverability, shorter takeoff roll, better pitch authority at high angles of attack, the ability to execute more aggressive sustained maneuvers at close range. That choice suggests something very important. The J-20 was not designed exclusively as a sneaky long-range missile truck that avoids close combat at all costs. It was designed to be able to fight at close range if close range happens. The canards are insurance. They are the J-20 saying, if the stealth fails, if the geometry of the engagement forces a visual range fight, I can still compete. Now look at the tail design. The J-20 has two large all-moving vertical tail fins, canted outward at an angle. From a stealth perspective, this is a significant feature. Vertical tail fins at certain angles relative to incoming radar are problematic. The F-22 solved this by canting its twin tails inward at a specific angle, chosen to deflect radar energy efficiently. The B-2 solved it by eliminating vertical tails entirely. The F-35 uses canted tails similar in concept to the F-22. The J-20's tail geometry is optimized in ways that are distinct from any of these solutions. Analysis of the angles suggests the design prioritizes certain engagement aspects over others. Specifically, the tail geometry appears optimized for the kinds of radar threats the J-20 is most likely to face in the scenarios its designers prioritized. Which brings us to the most important question: what scenarios did the designers prioritize? To understand the J-20's RCS choices, you have to understand the operational context China's military planners were thinking about when they designed it. The J-20 did not emerge from a vacuum. It emerged from a specific strategic situation. China's planners looked at the Pacific theater. They looked at the distances involved, they looked at the primary threats they expected to face, and they built an aircraft around a very specific set of mission requirements that differ from what drove the F-22 and F-35. Consider the geography. The first island chain, the string of islands from Japan through Taiwan through the Philippines, sits at distances from the Chinese mainland that make it very different from the European NATO scenario that largely drove American stealth design. In the Pacific, ranges are enormous. The distances from Chinese air bases to potential engagement zones around Taiwan or in the East China Sea or South China Sea are significant. An aircraft fighting in this environment needs range. It needs the ability to carry enough fuel and weapons to operate meaningfully at distance from home base. The J-20's large size, which creates RCS challenges, simultaneously gives it more internal volume for fuel. The J-20 reportedly carries more fuel than the F-22, giving it significantly longer range. That was a deliberate trade, size and range in exchange for the absolute minimum possible RCS. Now think about the primary threats the J-20 would face in that Pacific scenario. American carrier-based aviation, the F-418E-20 Super Hornet, the F-35C, E-2D Hawkeye Airborne Early Warning Aircraft, E/EACG Growler Electronic Attack Aircraft, long-range AIM-120D and AIM-260 missiles launched from F-22s flying combat air patrol, land-based F-22s operating from bases in Japan or Guam. The threat is primarily coming from specific directions, in specific scenarios, involving specific radar frequencies. The J-20's RCS optimization, including the choices that differ from Western stealth philosophy, makes more sense when you understand this context. The aircraft's frontal stealth is serious and genuine. Its side and rear aspect RCS is higher, as it is on every stealth aircraft. But the specific angular distribution of that RCS, the directions in which the J-20 is harder to see versus easier to see, appears tuned to the geometry of the engagements China's planners expected. there is another dimension here that is absolutely critical to understand. And that is the question of radar frequency. This is where the conversation gets deeply technical, but also deeply important, because frequency is everything when it comes to stealth. Radar systems used in air combat operate across a wide range of frequencies. Different frequencies are suited to different tasks. The X-band, roughly 8 to 12 gigahertz, is the standard frequency range for airborne fire control radars. It provides the resolution and accuracy needed to track a target precisely enough to guide a missile. Most fighter aircraft radars operate in this band. Most air-to-air missiles use X-band seekers or semi-active homing that relies on X-band illumination. Modern stealth aircraft like the F-22 and F-35 are specifically and carefully optimized to have extremely low RCS in the X-band. Their angular geometry, their surface coatings, their edge alignments are all chosen with X-band radar wavelengths in mind. Against X-band fire control radar, they are extraordinarily difficult to detect and track. But there are other frequency bands, and here is where things get uncomfortable for every stealth designer in the world. Lower frequency radars, specifically VHF and UHF band radars, operating at roughly 30 to 300 MHz and 300 MHz to 3 GHz respectively, do not work the same way against stealth aircraft. The relationship between radar wavelength and the size of the aircraft's features changes fundamentally at lower frequencies. At VHF and UHF frequencies, the wavelength of the radar signal approaches the physical dimensions of major aircraft features: leading edges, wingspans, fuselage lengths. When this happens, a phenomenon called resonance scattering occurs. The aircraft essentially resonates with the radar wave in a way that produces a much stronger return than standard high-frequency stealth techniques can suppress. In simple terms, some stealth aircraft that are nearly invisible to X-band radar are significantly more visible to VHF and UHF radar. This is not a secret. The US and its allies know this. Russia's Nebo-M radar system is specifically a VHF radar designed to detect stealth aircraft. China has its own long-range, low-frequency radar systems designed for the same purpose, and in the ongoing chess game of stealth versus radar, every designer has to choose how much effort to put into defeating which frequency bands, because you cannot optimize perfectly for all of them simultaneously. Every choice is a trade-off. Now here is the analytically interesting question. How has China optimized the J-20 against different radar frequency bands? And is that optimization different from what Western designers chose? The honest answer is that the precise details of the J-20's RCS across different frequency bands are classified. Nobody outside the People's Liberation Army Air Force and Chengdu Aircraft Corporation knows the exact numbers. But based on observable geometry, on statements by Chinese engineers that have been collected by analysts, on the behavior and employment patterns of the aircraft in Chinese exercises, and on the physics of what different design choices produce, analysts have developed a reasonably confident picture. The J-20 appears to have been designed with a somewhat different balance between X-band optimization and lower frequency performance than the F-22 or F-35. The F-22 pushes X-band frontal RCS to extraordinary lows. The trade-off accepted is that at some other frequency bands and angles, the RCS is higher. The J-20 appears to have made slightly different trade-offs, not necessarily worse in absolute terms, but different, oriented around a different threat set, a different geometry of engagements, different radar environments the aircraft expects to operate in. One specific area where analysts see this is in the design of the J-20's fuselage blending and surface curvature. The F-22 uses flat facets arranged in carefully calculated orientations. The J-20 blends curves and facets in ways that are somewhat different, suggesting a somewhat different optimization target. Not necessarily a less sophisticated one, just a different one. And there is one more structural difference that matters enormously from a tactical standpoint. The J-20's overall RCS profile appears to be less symmetrical across engagement aspects than the F-22's. The F-22 was designed to be an air superiority fighter first. That means it needed to be hard to see from almost any angle that another fighter might approach from, because in a real dogfight, the geometry changes constantly. You might be head-on one moment and flank the next. The F-22's stealth attempts, within engineering limits, to be reasonably consistent across a broader range of aspects. The J-20, analysts believe, accepts larger variations in RCS across aspects and instead concentrates its stealth performance in the specific angular zones that matter most for its primary missions. What are those primary missions? Long-range penetration, standoff missile attack, targeting and degrading American airborne early warning and control aircraft, aerial refueling aircraft, and other high-value support assets that make American power projection work. More on that in a moment. Now, let us talk about the coatings. Because the physical shape of an aircraft is only half the stealth equation, the other half is radar-absorbent material, RAM coatings applied to the aircraft's surface that absorb incoming radar energy rather than reflecting it. Western stealth aircraft, particularly the F-22 and B-2, are notorious for the complexity and sensitivity of their RAM coatings. The B-2's coatings require careful maintenance in climate-controlled hangars. They degrade with exposure to moisture, heat, and physical stress. The F-22's coatings are similarly demanding. This is not a trivial operational issue. An aircraft that needs days of maintenance attention to its skin every time it flies has real operational availability constraints. In a high-tempo conflict, that matters. China has invested heavily in RAM technology. Chengdu and its associated research institutes have published significant technical literature on advanced radar-absorbing materials. Independent analysis of the J-20's surface treatments from the available photographs and from radar cross-section estimates derived from various observation angles suggests that the RAM applied to the J-20 is genuinely capable. But there is also evidence, based on operational patterns and maintenance observations at Chinese air bases, that China has worked hard to make the J-20's coatings more operationally robust than early Western stealth coatings were, more resistant to environmental degradation, easier to maintain in field conditions. This would be consistent with a military that is preparing for high-intensity conflict in the Pacific, where sortie rates matter and where the ability to keep aircraft flying continuously for days or weeks would be critical. There is also a question of coating optimization across frequency bands that parallels the shape discussion. The best RAM materials are frequency-specific. They are most effective at absorbing particular wavelengths. A coating optimized for X-band will not perform as well at L-band or S-band. China's choice of coating formulation, like its choice of geometry, appears to reflect a specific set of threat priorities. And those priorities, while overlapping significantly with American priorities, are not identical. Now let us talk tactics. Because all of this physics and engineering only matters in the context of what it means for how the J-20 would actually fight. This is where the analysis becomes truly gripping. The J-20's distinctive RCS profile creates a specific tactical reality. An aircraft built with this particular combination of strengths, genuine frontal stealth, long range, large internal weapons capacity, enhanced maneuverability via canards, and an RCS optimized for specific engagement geometries, is not built for the same tactical role as the F-22. They are stealth fighters, but they are stealth fighters of genuinely different character. And understanding that difference is essential for any force that might face the J-20. Consider the primary mission that almost every serious analyst assigns to the J-20. Force multiplication denial, or more specifically, ISR and C2 asset hunting. ISR stands for intelligence, surveillance, and reconnaissance. C2 stands for command and control. In modern American-style air warfare, everything depends on a small number of extremely capable support aircraft. The E-2D Hawkeye flying from carriers provides the radar picture that allows fighters to prosecute targets at long range. The E-3 Sentry AWACS provides theater-wide situational awareness. The E-8 J-Stars handles ground surveillance. The RC-135 family handles signals intelligence. The P-8 Poseidon handles maritime patrol, and the KC-135 and KC-46 tankers provide the aerial refueling that extends the range and endurance of every tactical aircraft in the fleet. Lose those support aircraft and the entire American air combat architecture degrades catastrophically. F-22s without tanker support have a fraction of their operational range. F-35s without data link feeds from E-2Ds or AWACS lose much of their situational advantage. The entire system depends on these high-value, relatively slow, relatively non-stealthy aircraft flying in protected orbits and enabling everything else. The J-20 appears to have been sized, ranged, and armed, specifically to threaten those aircraft. Its range, significantly greater than the F-22's, allows it to reach the orbits where these support aircraft typically fly. Its large internal weapons bays, estimated to be capable of carrying up to 6 or more long-range air-to-air missiles, including the PL-15, with a range estimated at over 200 kilometers, give it the firepower to conduct multi-target engagements. And its frontal stealth, in the scenarios where it is approaching from angles that favor its RCS optimization, makes it difficult for the very radar systems it is trying to destroy to detect it early enough to respond. This is not a speculative scenario. Chinese military doctrine explicitly discusses the importance of degrading the enemy's information superiority and C4ISR architecture as a first priority task in any conflict. The J-20 is the physical embodiment of that doctrine. It is a long-range, stealthy, missile-armed hunter, specifically designed to cut the threads that hold American air power together. Now think about what that means for the tactical picture. If China were to initiate a conflict in the Taiwan Strait, the opening hours would likely see J-20s operating at long range, using their frontal stealth and long-range missiles to target the AWACS, the Hawkeyes, and the tankers that American tactical aircraft depend on. If successful, even partially, this would force American fighters to operate with degraded situational awareness, shorter ranges, and reduced coordination. The J-20s themselves, having completed their initial strikes, might then be positioned to engage fourth-generation fighters, like Super Hornets, that are suddenly operating blind, without the radar coverage and data link support they depend on. Against those fourth-generation aircraft, the J-20's canard-enhanced maneuverability matters. Once the long-range stealth advantage of the initial engagement has played out, once the ranges close and the missiles have flown, the fight could transition to closer range. And at closer range, canards are real. The J-20's enhanced pitch authority and sustained turn rate, improved by those canard surfaces that Western stealth purists rejected, give it a genuine edge in close-range visual or near-visual range combat. This is the tactical coherence of the J-20 design. It was not built to simply copy the F-22's approach. It was built to execute a specific operational sequence that exploits its strengths against the specific force it expects to face. Long-range stealth for the opening strike. High-value target engagement at extended range with large missiles. Then, if needed, close-range maneuverability to finish or survive. Against the F-22 directly, the calculus is different and far less favorable for the J-20. The F-22 has lower frontal RCS. It has supercruise capability, the ability to fly at supersonic speed without afterburner, giving it a significant energy advantage. Its thrust vectoring nozzles provide close-range maneuverability that can match or exceed canard-equipped designs in certain regimes. And it carries 6 AIM-120 AMRAAMs plus 2 AIM-9X Sidewinders internally. A direct F-22 versus J-20 engagement at long range heavily favors the F-22. The Raptor's lower RCS means it can achieve a weapons quality track on the J-20 before the J-20 has an equivalent track on it. In beyond visual range air combat, that time advantage is often decisive. The side that shoots first with a high-confidence track typically wins. The F-22 can shoot first. It is built for exactly that. But here is the uncomfortable reality that American planners have to confront. The F-22 fleet is small. There are fewer than 200 F-22s in existence. Of those, only around 130 to 140 are operational at any given time. In a Pacific conflict, only a fraction of those would be positioned close enough to the fight to be operationally relevant in the early phases. China has rapidly expanded its J-20 fleet. Estimates in 2024 suggest China has between 150 and 200 J-20s in service, with production continuing at a pace that could push that number significantly higher within a few years. The J-20 fleet is growing. The F-22 fleet is fixed. That asymmetry matters in a sustained conflict. And here is another dimension of the tactical picture that is rarely discussed. The J-20 does not need to defeat the F-22 in one-on-one combat to be strategically effective. It needs to impose costs. It needs to occupy F-22 resources. If J-20s are operating deep in the battle space threatening support aircraft, every F-22 assigned to protecting tankers and AWACS is an F-22 not available for offensive counter-air operations or strike escort. The J-20 forces a resource allocation problem on the American side that is itself strategically valuable, regardless of the outcome of any individual engagement. This is sophisticated strategic thinking embedded in an aircraft design. The J-20's RCS profile, its size, its range, its weapons load, its canards, all of it reflects a coherent theory of how to fight a peer opponent with superior individual aircraft quality by imposing dilemmas rather than seeking direct equivalence. Now let us talk about the sensor suite. Because stealth is only half the coin. The other half is sensors. A stealthy aircraft that cannot see the enemy is only half the solution. The J-20 was originally fielded with the Russian AL-31F engine, the same engine used in the Su-27 family. This was widely seen as a significant capability limitation. The AL-31F's large infrared signature, visible plume, and acoustic signature partially offset the aircraft's stealth characteristics. China has worked hard to field its own engine, the WS-15, which is reportedly at or near parity with Western high-performance turbofan engines and provides significantly better thermal management. The transition to domestic engines improves the J-20's overall low observable signature because engine exhaust is a significant detection vector beyond just radar. The J-20's radar is believed to be an active electronically scanned array, AESA, system designated the Type 1475 or KLJ-5. AESA radars are transformative for stealth fighters. Because they can rapidly change frequency, they are more difficult for enemy electronic warfare systems to jam. They can operate in a low probability of intercept mode that makes it harder for enemy radar warning receivers to detect that the J-20 is actively scanning. They provide longer range tracking and higher target discrimination than legacy mechanical or passive electronically scanned array radars. The J-20's AESA radar, combined with its data link connectivity to ground-based radar networks, space-based surveillance systems, and other airborne sensors, gives it a sensor picture that is substantially more capable than its external appearance in early photographs suggested. China has also invested heavily in what analysts call the EODAS, or Electro-Optical Distributed Aperture System equivalent. The F-35 has a system called the AN/AAQ-37 DAS that provides spherical infrared coverage around the aircraft, allowing the pilot to see in every direction through the skin of the aircraft via infrared cameras. There is evidence that the J-20 has incorporated a similar capability. This matters enormously for stealth aircraft because infrared detection is one of the primary countermeasures to radar stealth. If you cannot see a stealthy aircraft on radar, you might still be able to detect the heat from its engines with an infrared search and track sensor. An aircraft with a full sphere of infrared awareness is harder to sneak up on. It also allows the pilot to engage targets detected via infrared without activating the radar, which would reveal the aircraft's position. All of this sensor capability combines with the J-20's stealth to create what analysts call a first-look, first-shot advantage in many engagement scenarios. The J-20, flying in a low observable mode, using its AESA radar in low probability of intercept mode or relying on data link feeds from off-board sensors, can potentially generate engagement quality data on a target without that target knowing it is being tracked. It then fires a long-range PL-15 missile and either maintains position or turns away before the enemy radar has a solid enough track to generate a return shot. The PL-15 itself deserves discussion. This is not a legacy Chinese missile. It is a genuine long-range, active radar-guided, AESA seeker-equipped air-to-air missile, estimated to have a range of 150 to 300 kilometers, depending on launch parameters. This range likely meets or exceeds the AIM-120D AMRAAM's effective range. China is also developing the PL-21, an even longer-range missile designed specifically to target high-value support aircraft. When the J-20 fires a PL-21 at an AWACS or tanker, from a distance at which the target's radar has not yet resolved the J-20 as a trackable threat, that is a realistic scenario. Not a hypothetical, a genuine tactical possibility that American force planners have to account for. Let us shift and talk about one more critical dimension of the J-20's RCS situation that gets almost no attention in popular coverage: the question of RCS from below. In most air combat discussions, people talk about frontal and side aspect radar cross-section because those are the aspects most relevant to radar systems mounted on other aircraft or on the ground looking horizontally. But there is a growing category of threat that looks up at aircraft from below. Ground-based bistatic radar systems, coastal radar installations, submarine launch systems, shipborne radars at low elevation angles, and increasingly, low-frequency radar systems that look for the underside of aircraft to find stealth features that the upward-looking top surface conceals. The underside of a stealth aircraft is a complicated surface. It has weapons bay doors that open during employment. It has inlet geometries that contribute to lower hemisphere RCS. It has structural joints and panel lines that, in any stealth aircraft, are a source of potential radar return if not precisely managed. Analysis of the J-20's underside geometry, visible in photographs taken from below during airshow appearances, shows careful attention to panel line alignment, inlet geometry on the underside, and surface blending in the lower fuselage. But the presence of the large internal weapons bays, necessary for carrying significant missile loads, creates challenges for lower hemisphere stealth that no current stealth aircraft has entirely solved. This is one area where the J-20, like every other stealth aircraft in existence, makes compromises. The weapons bays are large. They have to be to carry the PL-15. Large bay doors, when open, create significant radar returns. Every stealth aircraft in the world, including the F-22 and F-35, experiences a temporary spike in RCS during the seconds when its weapons bay doors are open for a missile launch. The solution is to open doors, launch rapidly, and close. But in the seconds of exposure, the aircraft is detectably more visible. Tactical employment accounts for this, but it is a real constraint. Now let us bring this back to the broader strategic picture. Because the J-20 does not fight alone, it fights as part of a system, and that system is designed in ways that amplify the J-20's particular strengths while compensating for its limitations. China's air defense architecture is built around a layered, networked approach. Ground-based long-range radar systems, including VHF systems like the YLC-8B and the JY-27A, provide wide-area surveillance that can detect stealth aircraft at ranges where their higher RCS at low frequencies makes them visible. This ground-based radar picture is fused into a common air picture and distributed to airborne assets, including the KJ-500 and KJ-2000 AWACS aircraft, and to the J-20 via data link. The J-20 does not need to use its own radar to find targets in many scenarios. It can fly silently, relying on externally provided targeting data, and remain electromagnetically quiet until it is time to shoot. This networked employment model is critical to understanding the J-20's RCS priorities. When the aircraft does not need to illuminate targets with its own radar because ground-based or airborne sensors are doing that work, the only RCS that matters is the one that the enemy's radar sees. And in the geometry of likely engagements, the J-20's frontal stealth is optimized for exactly the angular aspects that would be most frequently presented to the threat radars it is most likely to encounter. Compare this to the F-22, which was designed in an era when networked warfare was less developed and when the assumption was that the aircraft itself would need to find, track, and engage targets largely autonomously. The F-22's radar and sensor suite is extraordinary. But the J-20 was designed into a world where the individual aircraft is one node in a much larger network. The individual RCS requirements can be set at a somewhat different level because the network provides coverage that the aircraft does not need to generate alone. This represents a fundamentally different and in some ways more modern design philosophy. There is a parallel here to the difference between the F-22 and the F-35 in American thinking. The F-35 was explicitly designed as a networked node. Its sensors are extraordinary, but they were designed to share data, to operate as part of a team, to see with the eyes of the entire network. The F-22 was designed to be the apex individual predator. The J-20 is closer to a hybrid. Individual stealth performance that is genuinely impressive, combined with a deep integration into a network architecture that fills its gaps. What does all this mean for the forces that might face the J-20? This is perhaps the most important question, and the answer is uncomfortable. The J-20's existence forces a fundamental reassessment of how American and Allied air power operates in the Pacific. The tactics, procedures, and force employment concepts that were developed in the context of fighting fourth-generation threats need significant revision against a stealthy, networked, long-range threat. The specific areas of concern are serious and concrete. High-value asset protection becomes vastly more complex. AWACS and tanker aircraft that have historically operated with relative freedom because fourth-generation threats could not reach them without being detected and intercepted far forward, now face a threat that might approach from unexpected angles with limited warning time. The radius at which these assets orbit and the fighter protection assigned to them needs to be fundamentally reconsidered. The range calculus of the entire fight changes. If tankers must orbit further from the threat due to J-20 risk, the tactical aircraft that depend on them get shorter legs and less time on station. This reduces sortie rates, reduces coverage, and compresses the options available to commanders. The J-20 does not need to kill a tanker to impose a cost. Simply by existing and by demonstrating the capability to threaten high-value assets, it forces a more conservative operating posture that degrades American effectiveness even when no shots are fired. Electronic emissions discipline becomes more important. The J-20 hunting with passive sensors and data link, looking for the radar emissions of fighter aircraft and support assets, creates pressure to minimize electromagnetic emissions across the entire force. Aircraft that emit less are harder to find. But aircraft that emit less also have less situational awareness individually. This is a genuine tension with no easy resolution. The F-35's role becomes more important, not less. The F-35 is not an F-22. It cannot supercruise. Its maneuverability is inferior in some regimes. Its frontal RCS is somewhat higher. But the F-35 is numerous. There are already hundreds in service across the US and Allied air forces, with plans for over 3,000 total. The F-35's extraordinary sensor suite and network connectivity mean that a formation of F-35s with good data link discipline can cooperate in ways that compound their collective effectiveness. Against J-20s, F-35s operating as a network team, with shared sensor pictures and cooperative engagement, could generate a combat capability that exceeds the sum of individual platforms. The tactics for this kind of collaborative combat are being developed and refined right now. The B-21